My name is Grace Muka, and this is my Lab 2 report for Physics 2211. In this report, I will first go over Newton's second law and the forces used, then the goal of the lab and the formulas used. I'll show the experiment and tracker in my data and glow script and compare the two. Finally, I'll discuss observations and consider some questions. Newton's second law states that the acceleration of an object is produced by a net force that is directly proportional to the magnitude of the net force, in the same direction as the net force, and inversely proportional to the mass of the object. The acceleration of the water bottle was affected by its mass and net force. The mass of the bottle has an inverse effect on the acceleration, meaning if the mass increased, the acceleration would have decreased and vice versa. The forces acting upon the object in this lab were the force of gravity, a downward force that the Earth exerts on an object. This is represented by F equals mg, where m is the mass of an object and g is the acceleration due to gravity, which is in the negative y direction. The drag force, a force acting opposite to the relative motion of an object with respect to the air, was also involved. This acted in the positive y direction. The goal of Lab 2 is to use Newton's second law and the momentum principle to describe the motion of an object dropped from rest that falls straight down somewhat slowly with a non-zero net force. I'll compare the results to a computational model for the motion and describe any discrepancies between predicted and actual data, and show the results of the lab where the predicted and observed model were very close together, and the velocity without accounting for the drag force was slightly faster. These are the two formulas that I use, the velocity update formula to calculate the new velocity of an object, and the position update formula to calculate the new position. Here are screenshots from my GlowScript program of the formulas in my code. The velocity update formula can be derived from the momentum formula on the right because momentum is equal to mass times velocity and the net force is not equal to zero. Momentum is relevant because the object's velocity was dependent on its mass. In this lab, I measured the change in velocity as a result of a non-constant force on an object, being the sum of the force of gravity and drag force. The object had a non-constant velocity, a result of the net force not being equal to zero. The system was the dry eraser and the surroundings were the lab classroom, and the initial conditions were the object being held in my hand with no velocity, set at the origin. We dropped it next to a meter stick and tracked its downward movement. Here is my XY axis and this is my video. At first, I was having issues with my data because I didn't calibrate the dimensions of the video with the meter stick, but my data was accurate after doing so. After I tracked the movement of the eraser, I got the experimental graph and data seen on the right. In this GlowScript code, we only consider the force of gravity acting on the object and disregard the drag force. Here are the initial conditions I set. The force of the gravity is the g constant, 9.8 meters per second, multiplied by the mass of the object, and is in the negative y direction. I calculated the mass on the eraser in SI units here, and the acceleration due to gravity constant is here. Here is the drag force coefficient, which I set to 0, which makes the net force only reliant on the force of gravity or the weight of the eraser. I also set the time constraint of the while loop to be the last reported time in tracker. When you run the model, the force acting down on the object is the force of gravity, which is constant. The position versus time graph is seen here in the negative y direction, but it's not a straight line because the net force isn't equal to 0, so velocity is not constant. Here's a more accurate model accounting for both force of gravity and the drag force. These act in opposite directions, F grav in the negative y direction and F drag in the positive y direction. The magnitudes aren't equal, so the net force isn't 0, meaning the object's velocity is not constant. The code here is the same as the code I just showed, except I set the B constant for the drag force to be 0.005 newtons, which accurately represented the drag force in the experiment. The drag force is then included in the net force formula, calculated here as the sum of the force of gravity and the drag force. When you run the code, the graph looks very similar to the last code because F drag is so small. The velocity in the negative y direction increases with time as position moves in the negative y direction. The object moving downward in this model and the resulting graphs are here. The drag force isn't seen in this diagram because it's so much smaller than the force of gravity, making it hard to see, which is why the eraser is still able to fall to the ground. Here is the expected and experimental data with and without drag. The graphs of the two data sets line up almost perfectly, which is how I expected. And the set without drag is slightly off because the object would move slightly faster with no drag force acting on it. Any discrepancies could be from not exactly selecting the middle of the object when tracking it, or the object moving slightly in the 0x direction, not solely y. The eraser fell with non-constant velocity due to non-zero net force from F grav and F drag. F grav was much stronger than F drag, hence why the object still fell at a high velocity. And an accurate value for F drag was 0.005 newtons. No drag force results in a faster velocity. The velocity versus time with drag had a non-constant force because F drag increases with velocity. Velocity versus time without drag is constant because F grav is constant. However, the model with drag most closely predicts terminal velocity because the forces are slightly closer to being balanced. Terminal velocity happens when the force of drag pointing up has exactly balanced the force of gravity pointing down. So F net equals 0. If the velocity was initially thrown downward, the terminal velocity would be greater than the case where the same object was initially dropped from rest, meaning that the object would need to decelerate instead of accelerate to reach terminal velocity, so there'd need to be a greater force in the positive y direction. Thank you for watching my Lab 2 report.